Today we're going to continue our study of normal distributions by talking about something called a z-score. A z-score measures how many standard deviations above or below the mean a raw score is. So we're measuring distance from the mean in standard deviations. The z-score is positive if the data lies above the mean, and the negative if the data value lies below the mean. When a set of data values are normally distributed, we can standardize each score by converting it into a z-score. Z-scores make it easier to compare data values measured on different scales. That's really the power of a z-score. Let's see if you understand. A data set has a mean of 50 and a standard deviation of 10. What is the z-score for each data value below? So think about that for a minute. A z-score is the distance away from the mean in standard deviations. So 60 is 10 above 50. Well, 10 is our standard deviation. 60 is one standard deviation above the mean, so its z-score is plus 1, positive 1. 70 is two standard deviations above the mean, so its z-score is plus 2. 40 is one standard deviation below the mean, so its z-score is negative 1. 20 is 3 standard deviations below the mean, so its z-score is negative 3. 50 is the mean, so it's no distance from the mean, so its z-score is 0. 65 is 1.5 standard deviations above the mean. 50 plus 10 is 60, plus half of a standard deviation 5 gets me to 65. So 65 has a z-score of positive 1.5. And finally 25 is negative 2.5 standard deviations below the mean, so it has a z-score of negative 2.5. There is a formula for a z-score, and there it is. A z-score is the data value you're talking about minus the mean over the standard deviation. This is written with population notation. We can use sample notation as well, depending on the context of the problem. Make sure you learn your z-score formula. It is not given to you on the Regents reference sheet. Okay, so let's do a few examples and be done. So suppose an SAT scores among college students are normally distributed with a mean of 500 and a standard deviation of 100. If a student scores a 700, what would her z-score be? Again, you should always draw a normal model and label it and flag it and then show your formula. Distribution with a mean of 500 and a standard deviation of 100. So you want to draw your model. Go a couple standard deviations above and below the mean. And we were curious about a z-score for our value of 700. So that's my flag value. Well, based on what we learned yesterday, we really already know the z-score. My mean is 500. This is 2 standard deviations above the mean. So 700 has a z-score of 2. To practice the formula and to see that we're telling the truth about the formula and that it's not magic, remember z is your flagged value minus the mean divided by the standard deviation. So here my flagged value is 700 minus my mean of 500 divided by the standard deviation of 100. 700 minus 500 is 200 divided by 100 is indeed 2. So that confirms that my z-score is 2. Again, one of the most powerful aspects of a z-score is that it drops or standardizes units. We can now compare data with different scales. So here's our second example. I have a set of math test scores with a mean of 70 and a standard deviation of 8. English test scores have a mean of 74 and a standard deviation of 16. I score a 78 on my math test and a 78 on my English test. So which test did I actually do better on? Let's use z-scores. Score on a test was 70 with a standard deviation of 8, In my English class, the mean was a 74 with a standard deviation of 16. I got a 78 on my test in both classes. Which one did I actually do better in? Well, let's find z-scores and talk about it. So my z-score for my math is 78 minus 70 divided by 8. That's 8 divided by 8, or 1. So I have a z-score of 1 on my math test. I'm 1 standard deviation above the mean. In English, I have 78 minus 74 divided by 16. So in English, 78 minus 74 is 4 divided by 16. That's 0.25. So in English, my z-score was 0.25. So let's think about that. If you draw our normal model, 1 standard deviation above the mean's up here. That's a z-score of 1. 0.25 standard deviations below the mean is here, much closer to average. So I did better on my math test because I was 1 full standard deviation above average, whereas on English I was only 0.25 standard deviations above average. That's the power of a z-score. It's being able to compare how you did in something and many other things. Not just grades, but in terms of grades, being able to compare how you did, same score, but with the mean and the standard deviation, you really get a sense of how well you did compared to everybody else. So let's talk about this problem. What will be the miles per gallon for a Toyota Camry when the average miles per hour, or per gallon, sorry, is 23? I know its z-score is 1.5, and the standard deviation is 2. So in this kind of problem, I know the mean, the z-score, and the standard deviation. What I don't know is the actual data value. But we are in algebra. We have a formula. The formula has 4 parts. We know 3 of them. We can solve for the 4th. So let's write our z-score formula. It's the data value minus the mean divided by the standard deviation. Plug in what you know, solve for the rest. Z is 1.5 equals, I'm looking for the data value, minus the mean of 23 divided by the standard deviation of 2. Cross multiply. 3 is x minus 23. Add 23 to both sides. I can expect that my Toyota Camry gets about 26 miles per gallon. Okay, here's our last example. I have a group of data with a normal distribution. It has a mean of 45. One element of the data is 60. Will its z-score be positive or negative? Well, all you need to know there is that 60 is larger than the mean. So that 60 would have to have a positive z-score because it's greater than, it's farther from the mean in the positive direction. So that will have a positive z-score. There you go. And that's it for tonight. You need to practice your z-scores a little, and we'll do lots more in class tomorrow. Have a good night.